Assalamu alaikum. Hi everyone. In the previous video, we have seen the general concept of realizing the mathematical logic expression in which the combinational logic devices have been utilized. Assuming the sum of product form being used, we began with utilizing the basic logic gates to realize the logic expression like this. And then we use the more structured device, which was the decoder. Here is the decoder that has been used. And of course, we utilize two OR gates to complete the design. And then we came to the utilization of the programmable logic device, in which we assume there were more output involved in the system, which is now we have Y and Z. Alright, in this video, I will show three simple examples of problem involving PLDs, in which one problem for each type of PLDs. But it's worth to mention that for the sake of this lesson, the size of PLDs used in the upcoming examples are not the same with the practical PLDs, because the actual PLDs could contain around 50 to 100 or more number of gates. Alright. Let's begin with this example, which regard to PROM. But first, we need to be conscious of which array in a particular PLD is fixed and which array is programmable. So since this is a PROM, we know that we can only decide the connection in the OR array, because the OR array in PROM is programmable. We can only decide the connection in the OR array because the AND array is already defined by the manufacturer. This can be seen from the dot symbol being used to indicate the connections of this intersection. So now the problem is, we are given two logic functions in the form of sum of minterms for Y and Z. All right. Firstly, we need to realize both functions using the given 3 input 2 output PROM. The top part of a PROM is in fact a decoder, which means if there are 3 input lines, there must be 8 AND gates, because 8 product minterms need to be generated. Secondly, the outputs expression are given in the M notation, like here. If we rewrite Y and Z, we get Y equals to M0, which is A bar, B bar, C bar, or M1, A bar, B bar, C, or M2, A bar, B, C bar, or with M5, A, B bar, C, and finally or with M7, A, B, C. And for Z, Z equals to M1, which corresponds to A bar B bar C, or M2 corresponds to A bar B C bar, or M4 A B bar C bar, and or with M6, which is A B C bar. Okay, now we have rewrite y and z in terms of Boolean algebra. We might think, why not we use the K-map to get the minimal sum, like we often did. Here I'll show you why K-map doesn't help when dealing with PROM. This is because if I build the K-map for y and z, so this K-map is for y and this is for z, and then I label here A, B, C. So this is 0, 0, 0, 1, 1, 1, 1, 0. Similarly here. Okay, then y equals to M01257. So 01257, z equals to sum of M1246. 1246. Here 0, 1, 2, 4, and 6. All right. Then, if I take this, for example, this as a group, and then this one, and then this for y, then I get y equals to A bar C bar, or AC, or A bar B bar, and then I get Z, let's say here, and here. Z equals to AC bar, or BC bar, or A bar B bar C. Okay, I get these minimal sums, which looks appealing because they are more compact as compared to the sum of minterms, as compared to this sum of minterms. But unfortunately, this doesn't work with PROM because the n array in PROM is fixed, that already produces the fixed product terms. So the right way to deal with PROM is by using the standard sum of product terms or minterms directly, or by referring to the truth table, such that let's open this. Such that if this is A, B, and then C, the leftmost AND gate produces A bar, B bar, C bar, that corresponds to M0, followed by A bar, B bar, C, A bar, B, C bar, A bar, B, C, A, B bar, C bar, A, B bar, C, A, B, C bar, and the rightmost gives A, B, C, that corresponds to M7. Okay, since y is the sum of M0, 1, 2, 5, 7. Y is the sum of M0, M1, M2, M5, and M7. We simply, so here this is Y and this is Z. So we simply choose this connection for Y, which is M0, M1, M2, M5, and M7. And similarly for Z, which is the sum of M1, M2, M4, and M6. So we choose M1, M2, M4, and M6 for Z. So this is how we deal with the PROM, in which we directly take the standard sum of products or the sum of minterms based on the function, rather than using the minimal sum based on the K-mat. Now let's turn our attention to the second example that involves the PLA. In this example, we are assigned to realize two logic functions, namely P and Q, using a 3x4x2 PLA. So what does 3x4x2 means? That means this PLA has 3 inputs, 4 AND gates, and 2 OR gates that equals to 2 outputs. Alright, as we have seen previously, both AND array and OR array in PLA are programmable. So the number of AND gates in a PLA is often less than the number of AND gates in a PROM, even though they have the same number of inputs. This is because since the AND array in the PLA is programmable, the user or designer has more freedom to form the product's terms, which are not necessarily the minterms. So logically, this should reduce the number of required AND gates. So back to the problem. Since the AND array of the PLA is programmable, finding the minimal sum using the K-mat might be very useful here. So let's proceed with the K-mat for both functions P and Q. Here are the map. So this is for P and this is for Q. So labeling the denoting the column label A, B here and C here. And label the coefficients, and we filling out the values, in which P is M0, 1, 3, 5. So here, 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 and here, and Q equals to the sum of M3, 5, 7. Which is 3, 5, and 7. Okay, now let's see what happened if we form the groups for values 1 with the largest possible group. This with this, let's use different color, this with this, and this one with this one for P, and for Q this with this, and this one with this. Here notice that how many unique product terms between the two functions P and Q. Now let's write P equals to A bar, B bar, then followed by A bar C, A bar C, followed by B bar C, and Q equals to BC or AC. Okay, here notice that how many unique products term between the two functions P and Q. Obviously, there are 5, which means 5 AND gates are required. But our problem is the provided number of AND gates in the given PLA is only 4. So how to make this possible? So here we can say in general the minimal sum derived from the K-map does not always help to solve the realization problem for a PLA. But don't get me wrong here. I want to emphasize that the K-map is still useful, but it is not always being used to find the minimal expressions. Okay, now let's ponder these two K-map again. We know that we are dealing with the PLA, so maybe we can form a common product term between P and Q. If yes, this will be very good because we can utilize a single AND gate to produce the common product term for both output P and Q. In other words, we have saved the utilization of the AND gate in the AND array. Here, what if we break this group in P, the red group? Okay, and also break this group in Q, in Q, yeah. And then we let this one to stay in the group of itself. Similarly, we did this for Q. And then we rewrite the expression for P and Q. So this becomes A bar B bar or A bar C, or with now A B bar C because we have the new group, and similarly here A B bar C that corresponds to this group. Now C, we have a common product terms between P and Q, and now let's see how many AND gates are required. So the answer is 4, which is one for A bar B bar, one for A bar C, one for A B bar C, okay, and another one for BC. So let's map these terms right away on the PLA. Okay, let's label this as A, and then B, and then C, and the outputs are P and Q, and we want these AND gates to produce A bar, B bar, A bar, C, A, B bar, C, and BC. In order to produce this, we do this connection A bar, B bar, and then here A bar, C, A, B bar, C for this AND gate, and finally BC. So we do this connection in the AND array, and in the OR array we take which one for P? P equals to A bar, B bar, or A bar, C, or with A, B bar, C. And Q equals to A, B bar, C. Notice that we share these AND gates for both P and Q. Q equals to A, B bar, C, or with B, C. All right. So that's how we deal with a PLA. That is, we use the K-map, but for our mentality in using that K-map is more on forming the group that provides common product terms rather than form a large group to get the shorter expression. Alright, now we arrive at the final example in this video lesson, which is regarding the PAL. So the attributes of PAL is the opposite of PROM, in which for PROM its AND array is fixed, while in the PAL its OR array is fixed. So coming to this problem, we need to realize both functions f and g using this provided PAL. Alright, before we proceed, we need to inspect the specification of this given PAL. Notice that this PAL has 4 inputs, but the number of input variables that need to be realized is only 3, which is A, B, C. Moreover, this PAL has 3 outputs, but we only need to realize 2 outputs variables, which are F and G. Then let us inspect the fixed connection in the OR array. Notice that the top OR gate and the middle OR gate this one and this one, each of the inputs is connected with 3 AND gates, 1, 2, 3, and 1, 2, 3. But the input of the bottom OR gate can only carry a maximum 2 product terms. So this might become the challenge or constraint for us, because in this particular PAL, an output can only carry a maximum 3 product terms, that is for the top and the middle OR gates. Now back to the problem. Let's right away construct the K-map for both outputs, F and G. So this is the K-map for F, and this is the K-map for G, and labeling the column and row, and label the index for the column and for the row. And fill out the K-map with ones in which f equals to the sum of m1, 2, 4, 5, 7. So f is the sum of m1, again 2, 4, 5, 7. 1, 2, 4, 5, 7. And g is the sum of 0, 1, 3, 5, 7. So 0, 1, 3, 5, 7. And making the group for f, so obviously here let's use a smaller size, the smaller thickness. Here one group, and then here, and then here, and another one here for f, and for g one here and another one here. Okay, so let's write the expression for f and g. So f equals to a bar b c bar, or a b bar, or a c, or b bar c. And g equals to a bar b bar or c. So this group gives this group gives ac, sorry, this is bc here, so this blue group gives a bar b bar, this gives a bar b c bar. The green group gives a b bar, and the yellow group in f gives a c. Alright, so now here is the problem. F consists of 4 product terms, but as we have noticed just now, one output in the PAL can only afford 3 product terms. So how to overcome this? Now thinking of breaking the group to form common terms, also doesn't help, because for example, if we break this group, okay, and then trying to create the individual group, let's say not individual but this combined with this, and so we have 2 groups of 2. Now we rewrite this expression equals to a bar c or ac. To form the term AC so that this equals to the term AC in F. So this might be appealing, but this doesn't work, because if we assign let me remove this first. If we assign, for example here, AC here, it can only fit to one OR gate, which is this, and we cannot add more like adding here because we are not permitted to modify the connection in the OR array for PAL. So having the common terms between the outputs doesn't work for PAL. Now let's revert this back to the large group. Sorry. And building this group back, so we have A bar, B bar plus C. Alright, remember that this PAL has an extra input and output, so the correct way is to exploit this advantage for function f that has 4 product terms. Using some algebraic manipulation, let's denote the last 2 terms in f. Let's denote the last 2 terms in f as, for example, h, in which f now equals to a bar, b, c bar, or a, b bar, or h, in which h itself equals to a, c, or b bar, c. So this is our h. And now let's open this PAL diagram and label the inputs. Here we label the input with A, B, C, and we label the output with F, G. Also, we label the newly introduced variable h. So h is here. Now from the last expression, f equals to a bar, b, c bar, or a, b bar, or h. Now let these AND gates produce a bar, b, c bar, and a, b bar, and these produce h. So to get a bar, b, c bar, we do this connection. To get a, b bar, we do this. And the question is how to get h, how to produce h. We can get h by connecting this output, which is how to make this. Or by making this connection and connect it to the extra input. I apologize because this PAL diagram is too large, so I don't have blank space to show this connection. By the way, let's finish this first and then let me clarify this again. So the idea is we can get h by connecting this output that produce h, okay, to the remaining input. Then we place this connection in the AND array. So since this is h, so to get h for the third AND gates, we assign this connection, right? Now you see that we have produced f. F equals to a bar, b, c bar, or a, b bar, or h. And how about g? It's not a big problem because g only has two product terms. So if we let this AND gate to produce, because g equals to a bar, b bar, or c, if we let this AND gate to produce a bar, b bar, and another one to produce c, and the last one and another one to produce 0, okay, and we do this connection a bar, b bar, and then c, and how to produce 0? Okay, the way is by connecting all input lines in this AND gate, because as we have seen in the first part of this video lesson, that if all connection is made in all input lines for an AND gates are connected, the output for that AND gate equals to 0. Okay. I would like to address more about the connection that we made from the outputs to the inputs, which looks like a feedback connection. This is permitted because that connection is made externally, not internally. Now, imagine this. This is the IC of the PAL device, where the pins on the left side are the inputs and the pins on the right side are the outputs. Now we have connected the inputs with A, B, C, and we have connected the output to F and G. Here is the connection of H. That is from output pin number 3 to input pin number 4. Notice that we only made the external wire without changing the internal attributes of the PAL. Okay, so again, I apologize for this unclear connection in this diagram, because due to I don't have blank space in the boundary of the PAL. So now we have seen those examples. We have seen 3 examples, 1 example for each of the PLD. To conclude this video, I would like to restate that each of the PLDs, be it PROM, PLA, or PAL, each of them has special attributes that pose different kind of problem that requires different techniques of solution. Moreover, all the output that I provide in this video, all this function F, G, P, Q, and then here Y, Z, Y, Z, all of the functions are presented in the sum of minterms form, or so-called the small m notation. Because in fact, the Boolean functions can come in many different forms, like the max terms, the non-standard sum of product or product of sum, or the mix between the product and sum, and they can be presented in the simplified or non-simplified forms. So in future, you should expect to face more challenge in various kind of problems. Okay, so that's all for now. Thanks for watching.